Today I wanted to talk a bit about linear and combinatorial optimizations, which are two techniques to achieve an optimal solution in a given context or situation. Those two techniques don't have the same way to operate or the same conditions. So we'll start with the linear optimization. So it's a mathematical modeling technique. As I said, the goal is to determine the best possible outcome in a given situation. One of the frequent usage is the search of the maximum profit, for example, or the minimum cost in a production context. And for that, there are a few key elements. The decision variables, those are the elements we can play with to try to find the best result. So basically, those are the ingredients we put in a recipe, for example, the materials we are using to build something, and adjusting those values can give better or worse results. The objective function is the calculation of the target itself. So what we try to get as minimum or as a maximum, like the profit or the cost. It's a linear function that takes into account the other variables that we defined before and calculate a result based on those parameters. And for a solution to be optimal, it needs some constraints, otherwise it would always be good. So we express the constraints also with the linear functions, but more in equation way to give some maximum limit or some minimum requirement, for example. And including in those constraints, there is very often a non-negativity constraint, because in real world, we usually work with product or ingredients or resources, time, people, that cannot be really in a negative amount. So it's very often that there is a x and y equal or superior to 0 to make it consistent with the real world. So those constraints, they form say a polygon that shows the spectrum of the possible solution that respects all the constraints. And because they are linear functions, they show as straight lines that are delimiting the perimeter of this region, let's call it like this. And normally the solution we are looking for, they are supposedly inside or on the edge of this polygon, because those are all the couples of values for the variables that are respecting the constraints that we fixed. Just quickly, it's called linear because everything is very proportional in it. If we apply something on the input, it directly shows equivalent to on the output. And we can work with some decimal values, and that's what allows us to explore some cases where there is a lot or infinite possibilities, and still find optimal solution in a reasonable time, so to say. Some common application of this, logistic, transport, for example, finding the cheapest way or cheapest way to transport goods from factories to warehouses, for example. Finance in the investment, that's a good way to reduce or handle a bit the risks while maximizing the return on invest. That's used in this context. And the manufacturing that I evoked already before, where we try to maximize the revenue and for minimal cost, so to say. And one specific example of this, the blending problem, which is quite known actually. If we take the situation of a factory that produce juices, for example, based on two ingredients, A and B, the target would be to produce this final juice with the minimum cost. So using exactly the correct amount of juice A and B to have the lowest cost at the end, but respecting some constraint. Sorry. So we have just a few data, like the cost per liter of the ingredients, 60 and 80 cents, and some constraint that we have to respect. That the final product has 40 mg of vitamin C minimum or more, and we have also the amount per ingredient, and that's what will be taken into account to find the optimal dose. Another constraint on the sugar, it should not have more than 100 grams of sugar at the end per liter in the final product. And again, we have the values for the ingredients. So when we have this, we can model the math model using the X and Y variables. So those would be the decision variables I talked about before. To represent the quantity of juice A and juice B we will put in the mix. The objective function in that case would be simply the price of a liter of juice A multiplied by the volume we used, and the same for the juice B, and that would be the cost of the final product. And that's what we try to reduce. And the constraints are also expressed in a linear inequation in that case, where we see again the limits that we are imposing. So the global product should not be lower than 40 mg of vitamin C and not more than 100 gram of sugar. And we see the non-negativity constraint because we are working with juice and we cannot put a negative amount of juice in the mix. The minimum would be 0. When we have all this, we can see a graph where we can start drawing the lines representing the constraint. In that case, the blue one is for the vitamins, vitamin content, and the red one is for the sugar. Just pass quickly on this slide. So here we see that anything above the blue line, all the blue area, is respecting the vitamin constraint. Anything below the red line is respecting the sugar constraint. Everything respect the positive values because we are working in the positive spectrum of the graph. So the 0, 0 is at the bottom left. So all the values here are positive. And obviously the green area is where the constraint overlap, and that's the area where our valid solutions are located. As I said before, the optimal solutions are usually on the corners of this polygon. So in that case, since we see a triangle, there would be 3 of them at the beginning of blue line, beginning of red line, and where the 2 lines are crossing. So in that case, there is one solution that takes only juice B. We don't put any juice A. but we still try to get the minimum amount of sugar. So that's the beginning of the line blue, the blue line. And that gives us at the end a 79 cent per liter for the final product. So that's one possibility. We have something a bit similar with the maximum of vitamin, but still respecting the sugar constraint. So in that case, we have a €1 per liter solution at the end. And we have what's supposed to be the optimal mix, which is in that case 50-50 actually. That ends up in 70 cents per liter at the end, and that's where the two lines are crossing and the dot is pointing on the graph. So that's basically how the algorithm is trying to narrow the solution until finding the one that is supposedly optimal, again according to the constraint that we set. Then for the combinatorial optimization, we'll just go a bit quicker because it's more complex actually. But that's a subdivision of the mathematical optimization, which is a very wide domain. The difference here, we use discrete variables, which means we don't use infinite range of variables with the decimals and so on. It's usually integer or binary, 0, 1, left, right, true, false, as when we explore a graph and we take some directions. The search space is finite. That means we know all the possibilities. The only problem is we cannot list them because there are too many and we don't have the time and capacity for that. But in the concept, we could do it if we had the means to do it. So that's a big difference with the linear optimization. And the best structure, for this is usually the graphs, because it allows to explore all the possibilities. The most famous problems that are solved with this technique is the very well-known TSP, traveling salesperson problem, which is basically having a bunch of cities or places, location, and having to visit them once in one loop, so finishing at the starting point, which is the problem that all the delivery company are facing, I guess. Another one that's quite known as well is the backpack problem, where you have a container, a backpack, and you have a bunch of items that have a value in a price and a volume or a weight, depending on the parameters, and you are trying to fit as much value in the bag as you can without exceeding any of those limits. So trying to get the best of it. And the job scheduling is kind of the same, trying to allocate some resources or some tasks on the resources without using them too much or trying to save the resources. And that's also very common in the working world. And one specific example that comes from nature, actually, that nature did by itself is the ant colony optimization, where the ants are going for resources. So initially they spread from the starting node or from the nest, and they explore all the paths they can find initially until they find a resource that is interesting. In that case, they trace back to the nest thanks to the pheromones that they are dropping on the path. That helps them to go straight back to the nest. And because they drop even more on the way back, the path that they are using is getting heavier and heavier. In a graph system, it's actually putting some weight on the nodes to orientate the navigation. And because of this, more ants later will follow the same path, attracted by the same pheromones. And this path will slowly become one of the most reliable and one of the unique one to use by all the ends. There could be another place somewhere where the same phenomenon happens, and another path is also quite strong, but most of the time there is one. But that doesn't mean it's the absolute best. It depends on the condition, when the path was found, the timing, which end came back, and so on. But it's giving a good solution in any case for what they need. And this system has been reproduced in many other domains from the human society, obviously, because it's quite efficient. And the traveling salesperson prime, which is also very, very used. As I said, we have a number of cities. What we are trying to reduce is the cost of the travel through all those cities and looping back to the starting point. The cost could be time, distance, or traveling expenses, whatever. It's quite complex because for any number of city, you have a n-1 factorial divided by 2 possible routes. So in numbers that makes for 5 cities, it's already 12 possible routes. It's not that big, but still something. When we reach 20 cities, for example, we are already at 6 multiplied 10 power 16 routes. So it starts to be harder to brute force or to manually test it, right? So that's where we need some help. In that case, the combinatorial optimization is still quite heavy. So there are some tricks that helps to find something that's close to the good solution, but not necessarily always the best of the best. Can use a kind of linear algorithm, but using a mechanism that's called branch and bound to cut some branches when we see that they lead to a solution that's not going to be optimal because we found already something before that was more efficient. So we stop early and not explore the deep branch that definitely are already too much. It works for smaller sets, but it's still complicated for big sets because we still have to explore a lot, no matter what. There are some other methods in between where we just designate a way to weight or to estimate the directions and the targets. Like the nearest neighbor, for example, is just trying to get the node that has the shortest distance that we didn't visit yet as first choice always. So that we're forcing a bit the decision, and it can give some good results. Again, not necessarily the best. And after that, we go through the nature-inspired algorithm, like we saw the ant colony optimization or some genetics algorithm that were discovered in that domain. And that gives usually very, very good solutions, close to optimal. And then the real-world application of these TSP principles, the logistics, obviously, like as I said, like the delivery trucks, but also the school bus, for example, for the routes. Manufacturing, when we plan the best sequences for the machines, for example, to work fast and efficiently. In genetics, it's also used for the DNA fragmentation and sequencing. And what could be interesting sometimes for us as well is in the internet networking for the delivery of packets and so on. It has been used for decades now, I would say. And it's very well implemented, some pathfinding algorithm and so on. All this is using this combinatorial optimization as well. And yeah, that was it for the quick intro to those optimization techniques. Thanks for listening.